Hey guys, welcome back to my channel, and today we will discuss another concept of graph theory, that is matching. Okay, we will try to understand what matchings are with a real life analogy, and note matching is can be done on any type of graph that you have. Okay, so let us see the analogy of selecting lab partners. Okay, selecting lab partner. So, in a lab class, the teacher has asked the students to choose one lab partner. That is, two students can be lab partners. And you know that if a student is lab partner of a student B, that same student cannot be lab partner of another student C, right? So, yes. So, let us make a graph. Now, the teacher has a graph where the nodes are representing the students, and if two students they are willing or compatible to be lab partners, then we are joining them with the edge. Okay. So these students are willing to be partners with these students having edges with them or labors. Okay. So A, B, C, D, E and F. Okay. So now what is an can be an example of matching? So suppose A has been matched with B or made lab partners. Okay, A and B are lab partners. Then I know that any A and C cannot be lab partner, B and D cannot be lab partners, right? So I can make C and D lab partners, right? So this can be a matching. So in technical terms, matching would mean that we are selecting edges such that the two edges selected, any two edges selected in the set are not neighbors or not adjacent or having a student or a vertex common. Okay, so let us first matching is ABCD. Okay, now we will see the concept of a maximal matching. Note, in this set ABCD from the graph, can we make any more lab partners? uh, yes, we can make EF as lab partners. In this set only I can add EF, and no two students are common in any of the edges, right? So I can write EF over here, and we got a bigger set of lab partners. So this is an example of a maximal matching. That is the largest set of edges where no two edges are neighbors. Okay. Okay. So are there more matchings possible in this graph? Let's see. Okay, now we will see the concept of a maximum matching. I will write another matching, possible matching with green colors. Okay. So green color is representing a different matching. Okay, I will remove the first from this graph so that there is no confusion. Okay. Okay, we'll draw it with red. Okay, another possible valid matching can be this is D. Okay, DE. Then I cannot select CD, BD, right? Then what we can be select is AB, right? This is another one. AB and DE. Okay. Is this a maximum matching? Maximum matching means in this graph, whole graph, are there any more uh, matchings having more edges than M2? Yes, there is a matching M1 having 3 edges. Can we have any other matchings more than 3 edges? No. So, this M1 is also a maximum matching. Maximum matching. And this is uh, A, B, D, E. This is a maximal matching. See, I cannot add more edges, right? From here, I cannot add any edge, right? Here also, I cannot add any more edge to make it a bigger set. So this is a maximal matching. That is, it's the largest set of non-adjacent edges. But for the entire graph, this is not a maximum matching. There are more in this graph only there are other set of matchings which is having more than two edges. So this is not maximum, but it is maximal. I hope the definitions are clear to you now. Now we will see the concept of perfect or complete matching. Okay, see, in this M2 matching, are all the students having lab partners? A have a lab partner, B has a lab partner, D and E have a lab partner. But C and F, they are not lab partners. So it is not covering all the students. All the students, they don't have a lab partner. That means this is not a perfect matching. M2 is not perfect. Perfect or complete matching. So, a perfect or complete matching is a matching where all the students they have a lab partner, or all the edges selected are incident on all the vertices of the of the graph. Okay. So, I will draw the M1 matching again. A B C D and EF. Okay, see the first M1 matching A, B, C, D, E, F. In all the edges selected that we have selected, all the students or all the nodes have been covered. That means this is a perfect matching or a complete matching. Okay, so I forgot to tell you another technical term. Another technical term for this matching is independent edges. Okay, independent edges, that means independent edges means the edges which are not neighbors, or they don't have a student or a vertex common. Okay, now if I suppose this graph we called it a G, the original graph. If I erase all the edges which are not part of the M1 matching, then this will give us the matching graph. So matchings can be sets as well as graph. They are just representation, nothing else. So if I erase um, these non-matching edges, okay. So this is another graph. This is called a induced graph. What does induced graph means? Induced graph means uh, no, this is a subgraph, right? Induced graph would mean that if you select all the nodes, then whatever edges are between the nodes, they have to be part of the subgraph. Whatever edges were there present in the original graph G, right? Between A, B, C, whatever edges were there, they have to be selected. Then that will be the example of an induced subgraph. But this is not an induced subgraph, okay? So this is an example of subgraph where all the matching edges has been selected. Okay, so we'll just create the original graph G again. Now we will go for some of the properties of perfect matching. Okay, so a perfect matching, in the perfect matching I can draw all the vertices uh, in the matching edges. Whatever first vertices are there, A, C, E, we can take it in a first set. And I know that in a bipartite graph the edges are between the sets, and the second vertex or second child can be taken in another set. B, D and F can be taken in another set, and the edges or they are lab partners is represented across the set. So this is a perfect matching when represented like this creates a bijective function, that is one every student is uniquely matched with another student. Uniquely means exactly one lab partner, and that is unique. And onto means the all the students in the set B, they have a lab partner. Nobody is left out or not having a lab partner. Okay, so one observation: if you have a perfect matching in a graph, that would mean it is always true that you will have even number of students or even number of vertices. You cannot have a perfect matching with odd number of vertices, because every student is mapped with another student. So how many ever is in the first set has to be there in the second set as well, right? So if there are odd number in the first set, 3, there will be 3 on the second set as well, to total 6. That is an even number, right? But if you have even number of vertices, that does not mean, it is not true, that does not mean the graph will definitely have a perfect matching. Okay, that means in the graph there you observe that there are even number of vertices. You cannot directly conclude that there will be always be a perfect matching. We will see an example is that of a star graph. Okay, 1 2 3 4. Okay, yeah, so we have 1 2 3 4 vertices, and we will join it with edges. But observe, I will label the names A, B, C, D. Note, all the edges are neighbors, right? C is common vertex. So if you make the lab partner BC, now C cannot be anyone else's partner. So this is the maximal matching as well as maximum matching for this graph. And it had even number of students, still it is not a complete or a perfect matching. So yeah, that's all for this video. Hope you enjoyed this concept and understood in the real world perspective what it means. Please like and share and subscribe to my channel. And happy learning. Keep observing in your real world where graph theory can be applied. Bye bye and take care.